Hi everyone, I'm Weonjung Sohn and I'm a PhD student at University of Technology Sydney in Australia. Today I'd like to talk about the effect of hydraulic retention time on the nitrification of urine in pilot-scale activated carbon incorporated membrane bioreactor and its hydroponic application. As we already know, the exponential growth of the global population has resulted in a significant increase in fertilizer use over the last 6 decades, and this led to our higher dependence on synthetic fertilizers. Therefore, the global fertilizer market, as well as the Australian fertilizer markets, are also expected to grow significantly by 2030. In our current linear economy, the production of synthetic fertilizers poses a lot of major global environmental challenges. Given this situation, our urine is like liquid gold because it's rich in essential nutrients for plants, which are nitrogen, phosphorus, and potassium. By source separating urine and transforming urine into a fertilizer, we can close the loop to make a circular economy. And this can offset 13% of the global fertilizer consumption. However, direct use of urine as a fertilizer is not recommended because of smell due to volatile ammonia and has unwanted micropollutants and organics. Therefore, urine nitrification in an ultrafiltration membrane bioreactor with activated carbon can be an innovative solution to address these drawbacks. In the bioreactor, ammonia oxidizing bacteria AOB converts ammonia to nitrite, and then nitrite oxidizing bacteria NOB converts nitrite to nitrate, which lowers pH without any chemical addition. At the same time, by using ultrafiltration membrane, virus can be rejected and high organic content and micropollutants can be removed by the absorption on the activated carbon. Finally, nitrogen, phosphorus, and potassium can be recovered in one final product as a liquid fertilizer. However, one remaining challenge is a long hydraulic retention time, which makes the system large footprint and more energy consumption. Therefore, my research is focusing on overcoming this challenge, how to reduce the HRT of the MBR system and the optimization of the produced urine fertilizer to be an effective fertilizer for hydroponic plant growth. As you might already know, in one of the buildings at University of Technology Sydney in Australia has one of the largest urine divergence systems which can separate urine from waterless male uriners in every floor. This allows to easily collect the source-separated urine and urine processing in the MBR system, and finally, the application of produced liquid urine fertilizer, achieving nutrients in a circular economy. Our previous study showed that powdered activated carbon (PAC) addition to the MBR resulted in over 99% removal of 6 selected micropollutants and improvement in total organic carbon removal rate compared to the conventional MBR. In addition, our urine fertilizer produced from the MBR system has been applied in various hydroponic systems for different plants' growth in the last few years and shows that our urine fertilizer was comparably effective to the commercial fertilizer. Based on our lab-scale studies, we recently developed the pilot-scale compact MBR system, as can be seen in the photos here, which has a main display for controllers and an inside controller panel. This system has maximum 200 liters of MBR tank inside, together with 100 liters of effluent tank. This compact MBR system has been in the operation for over 200 days now, and this system is showing the feasibility of on-site urine treatment and fertilizer production system in a building or household scale, and the potential application to the urban agriculture systems. So in this pilot-scale compact MBR system, I focused on investigating the effects of different hydraulic retention time conditions on the nitrification and the following produced fertilizer effectiveness for the application in the hydroponics. Since the previous urine treating MBRs were typically operated at a pH-based feeding mode to achieve stable nitrification, the HRT was a dependent factor of nitrification rate. However, prolonged HRT was a main challenge and a barrier for the potential commercialization of the system. So, this study aimed to investigate the impact of fixed HRT under continuous feeding mode on urine nitrification performance, and the produced effluents from different HRT conditions having different nitrogen compositions were applied to hydroponic basil growth to see the optimal HRT threshold. This figure is showing the nitrification performance in the MBR system over the period of 160 days. During the first 96 days, including the startup time, the urine was fed into the reactor with pH-based feeding mode as typical, and the average HRT resulted in 7 days in phase 1. Then, from phase 2 to 4, the urine was fed continuously by intentionally operating at the reduced fixed HRT conditions, which were 5, 3, and 1 day. The result showed significant increase of nitrite concentration from 3-day HRT and further increase at 1 day of very short HRT. This systematic HRT reduction in each phase also showed gradual decrease in ammonia to nitrite conversion rate from 40, 30, 20, and 10% in each phase. We also conducted the microbial analysis of sludge samples from different HRT conditions, and the result showed the microbial diversity was reduced when the HRT reduced to 1 day in phase 4. The microbial composition at phylum level and genus level, especially the genera of AOB and NOB, showed significantly high AOB and inhibited NOB in phase 3 and 4, which caused the nitrite accumulation in the system. After that, the permeate from each phase has been collected for hydroponic test on basil growth in hydroponic system called HydroGarden, and we could see the final diluted treatment solution had different nitrogen compositions. However, the total nitrogen was maintained at 250 ppm across the hydrogardens for the comparison of the growth. The basil grown with different treatment solutions from each phase has been quantified in terms of fresh biomass yield and dry biomass, stem height, and roots to shoots ratio. As a result, the urine fertilizer produced from up to HRT 5 days showed comparable results to the one grown with the commercial fertilizer, which can be an optimal HRT threshold condition. However, the reduced HRT at 3 and 1 days showed inhibited basil growth, which means they might need additional treatment to reduce the high nitrite concentration. In conclusion, this study was conducted to evaluate the effects of different HRT conditions on nitrification performance and fertilizer effectiveness to support the potential commercialization of the compact MBR system. And the system acclimated well to 7-day HRT under pH-based feeding mode. However, as the HRT was systematically reduced, the ammonia to nitrate conversion rate decreased gradually in each phase, accompanied by increasing nitrite accumulation. The hydroponic application of urine-derived fertilizer revealed that the HRTs of up to 5 days provided optimal basil growth, showing results comparable to the commercial fertilizers. I'd like to thank ARC NICE Hub and Professor Sohn and Dr. Sharaf for supporting my research, and I also thank my group members. Thank you for listening.